Okay, welcome to Lesson 10, Linear Models. This is Module 6, and we will be kind of departing from scatter plots for this lesson, and then we'll return to them in Lesson 11. But in this lesson, what we want to do is, and you can read here under classwork for yourself if you want to pause and read it word for word, but I'm going to summarize what we're going to do in this lesson. So we're going to look at linear models, which you've been looking at. You've looked at scatter plots. You fit a line to the data, and then you found the equation of that line. And so this lesson, we're going to look at actual linear functions that have a numeric function with them instead of just a scatter plot. But we're going to look at more closely about the relationship between the two variables in these. Remember, these are bivariate, meaning two variables. And we're going to talk more about some terminology for variables. And we are going to do some predicting, or not predicting, but do some interpreting of the slope again and the y-intercept in the context of different problems. Okay, so before we do example 1, I want to look at some of that terminology. So we've got some variable terminology, and one that many of you are familiar with. And these are x and y are the variables that we use on the coordinate grid traditionally, but others, of course, can be used. And we've talked about the fact that x is referred to as the independent variable and y as the dependent variable. And in science, what that means is the independent variable is that thing that I get to choose. You know, I get to choose how much fertilizer to put on the plant, and maybe I want to vary it to see what the best, how I can get the best growth for different amounts of fertilizer. So my dependent variable would be that maybe the height of the plant. So the independent thing is the thing I choose. That's what makes it independent. I choose different values for it. And then I get something that I measure, which is the dependent variable. In statistics, there's other words for the same kind of idea. There's the explanatory variable and the response variable. And we're going to see examples of this. It's just a little bit different connotation. And the other pair that we'll see these all used is the predictor and the predicted. So so there's things I can predict based on other factors. Okay, so for instance, the predictor variable could be, thinking of a cooking context, the temperature of my oven, and then the predicted would be the time it takes to cook the roast or the chicken or whatever it is. So all of these are saying basically the same thing. The y variable in each case is something that gets measured, and it's we're going to predict this y variable based on a value of the x variable. So let's look at some examples of that. So let's go back to example 1. Predicting the value of a numerical dependent or response variable based on the value of a given numerical independent variable has many applications in statistics. The first step in the process is to identify the dependent variable and the independent variable, or the predicted and predictor variables. There may be several independent variables that might be used to predict a given dependent variable. For example, okay, so here's our example. If you want to predict how well you're going to do on an upcoming statistics quiz, one possible independent variable is how much time you spent studying for the quiz. So through the year, you know, you might have a week where you spent 3 hours, another time you spent 5, Another time you spent none. And then you could predict based on that what your quiz score might be. And then the question is asked, what are some other possible numerical independent variables that could relate to how well you're going to do on the quiz? Okay, so we want to predict how well we're going to do on the quiz, so what could be some factors? So besides time spent studying, an obvious one that your parents have probably told you before is how much sleep you got. Did you get enough sleep the night before the quiz? So that would be a numerical independent variable that could be used to predict your quiz score. Another one might be, it has to be numeric. I always think that a good breakfast on the day of a quiz is important. So maybe the number of calories that you have for breakfast could be a predictor of how well you do on the quiz. That might be a little out there, but you get the idea. Okay, so we're going to look at some of these and try to come up with some of our own ideas. Now, so let's look at exercise 1 first. For each of the following dependent response variables, identify 2 possible numerical independent explanatory variables that might be used to predict the value of the dependent variable. So these are backwards from how I would like to see. Normally I would like to see X on the left because that's how we usually write ordered pairs, but they've got this set up this way, so it's okay. So if I want to predict the height of a son of somebody, what could be an explanatory variable or something that might explain, I guess that's why we're using that would explain the height of the sun. So some obvious ones, and you can look in the answer key maybe for even more things like this, but the height, height of the father or the height of the mother could probably be a good explanatory variable that could be used to predict the height of a son. Number of points played in a game by a basketball player. Okay, so what would that depend on? The number of points scored in a game by a basketball player might be the number of minutes of game time. Minutes of game time would be one possible. Another one could be the number of times the ball was passed to that player. I don't know much about basketball, so... number of hamburgers to make for a family picnic. Okay, so what could be used to predict that? Maybe number of meat eaters in the family. Okay. So remember, our goal here is always prediction, is always... from my X variable, if I have a value for that, how can I predict the Y? Okay, so look at the next 2 on your own, maybe pause and then come back and we'll talk about them. Okay, so for the next one, time it takes a person to run a mile. I could say maybe wind speed. Because if the wind is blowing a lot, it might slow them down. There might be other things like the amount of practice that a person has had, practice running. Another one that your answer key has is height above sea level. The higher you are above sea level, the less oxygen there is, so it's going to be harder to run a mile. So those are all some explanatory variables that might be good ways to predict the time it takes someone to run a mile. Okay, amount of money won by a contestant on Jeopardy. We could say the amount of money won might depend on the years of education, or years of education of the contestant. What else? The amount of money won on Jeopardy might depend on the IQ of the contestant or the number of questions that they answered correctly. So, okay, so let's look at a few more of these. Maybe you could work on all 4 of these and then come back and I'll share my responses with you. Okay, so let's look at this next one. So the response variable Y, fuel efficiency in miles per gallon for a car. The weight of the car is a huge factor in this. So that might be a good predictor of the mileage, the weight of car. Okay, so that would be one. Let's see, a couple others would be maybe the size of the engine. Okay, number of honeybees in a beehive at a particular time. What could be an explanatory variable for that? Okay, my first thought would be the air temperature. When bees are cold, when the air temperature is cold, they tend to hang out in the beehive. The answer key here says the size of the queen bee. Okay, so a larger queen might have more bees in the hive. So size of the queen. Number of blooms on a dahlia plant. Okay, so this goes back to my opening example. The amount of fertilizer could be the independent variable for that. Amount of fertilizer or maybe water. That's given to the plant. Okay, so number of blooms. Number of forest fires in a state during a particular year. Okay, so this is for California right now. I'm thinking first thing comes to my mind is amount of rainfall. The amount of rainfall has an effect on the number of forest fires for sure. Okay, so you can see that for each of these response variables, there could be several different explanatory or independent variables that could be used to predict the response variable. Okay, we've got a few more. So this we're going to do backwards. Okay, so again, we've got our dependent variable and our independent variable, and so we're going to kind of turn it around. So if we know the age of a student, what could we predict based on the age of a student? Well, we could say maybe their height. We could predict their height. Age of a student, we could predict their reading score. The older they are, probably the higher their reading score. Okay, so those are a couple things, but you've probably thought of a lot more. Okay, what about height of a golfer? Maybe the distance they hit the ball. Well, whatever, that could be said less awkwardly. The distance of their drive when they do it. So maybe the taller the golfer, the further they could hit the ball. So what else could we predict from the height of a golfer? Number of holes in one, maybe. I don't know if they'd be more likely to get more or less or whatever. All right, amount of pain reliever taken. Maybe it could be the time for the pain to subside. Okay. Although I wouldn't recommend taking more than the dosage amount. So it's kind of an interesting example to have here. So number of years of education. How about the person's salary? The salary earned. Okay, so more education maybe could translate to a greater salary. Amount of fertilizer used on a garden. How about plant height, right? We talked about that would be one thing, plant height, or the number of the fruit harvested or something like that. Fruit harvest. We could maybe measure the weight of the harvest or something like that. Size of a diamond ring. If I know the size of a diamond ring, I can probably predict its price. Yeah. What about total salary for all of a team's players? Okay, so if we have a team that pays a lot for their players, maybe they're going to have a higher, well, let's see, we'll make it football. So it should, total salary, and we could say number of points scored per game. Okay, so can we predict the number of points a team is going to score by the amount they pay for their team players? I don't know. But we could do some data gathering and figure out if there is a correlation. Maybe there's not. Okay, so we're going to continue talking about independent and dependent variables, and we're going to also use this other new vocabulary. So you should probably have this written down somewhere. It's the handy chart. Independent, dependent, explanatory, response, predictor, and predicted. So they all have this idea that we can predict the value of y based on the value of x. Okay, that's not always the case, but when we can come up with a mathematical model, then it is. All right, so let's move on to example 2. Okay, so let's look at example 2. In this example, it's going to look very similar to examples you've done in the past, and it's just building your ability to explain the relationship between two variables and also be able to explain what the slope means in the context of the problem. And we've been doing that, but it takes a lot of practice for it to become kind of second nature. So that's what we're doing here. So let's read the example together, and then you can work on the exercises independently. So a cell phone company offers the following basic cell phone plan to its customers. Customer pays a monthly fee of $40. In addition, the customer pays 15 cents per text message sent from the cell phone. There is no limit to the number of text messages per month that could be sent, and there is no charge for receiving text messages. Okay, so you're going to look at exercises 3 through, 3 through 9 to start with, and see how far you can get with that in answering these questions. Do the ones you can, and then come back and we'll work through them together. Okay, so let's look at exercise 3. Hopefully this was pretty straightforward for you. Determine the following. Justin never sends a text message. What would be his total monthly cost? So he doesn't send any text messages, so all he has is the basic rate. So he's going to pay $40 per month. Okay, so part B. During a typical month, Abby sends 25 text messages. What is her total cost for a typical month? Well, it would be the $40 plus her text message costs. So she has 25 and they're each 15 cents. And so her total cost is going to be 40 plus 25 times 15, which comes out to $43.75. Okay, now Robert sends at least 250 text messages a month. What would be an estimate of the least his total monthly cost is likely to be? Well, so for Robert, he's got the same $40 plus 250 times the 15 cents per message. And so instead of $3.75, that's going to be $37.50. So plus 40 would be $77.50 per month for his phone bill. All right, so that was probably fine for you, pretty straightforward. Now, number 4, use descriptive words to write a linear model describing the relationship between the number of text messages sent and the total monthly cost. Okay, so this is what our textbooks before called a verbal model, basically. So we're just going to say total monthly cost is equal to, and I'm going to use the equal sign, is equal to $40 plus, and we'll say the number of text messages, so it's just what we did on those others, number of messages times 15 hundredths or 15 cents per message. So total monthly cost is $40, the flat rate, plus the variable rate, which is the number of messages times 15 cents. Okay, so I could use that formula to find the cost for any number of text messages. All right, so let's answer number 5 now. Is the relationship between the number of text messages sent and the total monthly cost linear? Explain your answer. Well, we have an equation for this. It's an exact equation, and I could use variables here to make it really clear. 40 plus, now if I use x for the number of messages, 0.15 times x, I can see that that is a linear function. It meets the requirements of a linear function because the power on the variables is to the first power. And this just looks like a slope-intercept form, doesn't it? Just kind of backwards here. I could turn these two terms around, and it would be slope-intercept, which I know always graphs as a line. Y equals mx plus b. And I can see the rate of change for every additional text message, the cost goes up by 15 cents. So that's kind of the definition of constant rate. And so there's a lot of things you could say to show that this is a linear relationship. Okay, number 6. Let x represent the independent variable and y represent the dependent variable. Use the variables x and y to write the function representing the relationship you indicated in exercise 4. Okay, so in exercise 4 was this. That was our descriptive or verbal model of this function. And got a little ahead of ourselves in number 5. But let's talk about what is the independent and what is the dependent variable here. In other words, what are we trying to predict? That's going to be our dependent variable. And what do we have control of? That's our independent variable. Well, we have control of the number, my color here. We have, the independent variable is going to be, sorry, pen's not working, number of text messages. Number of texts will be our independent variable. And then our dependent variable is going to be what we're going to predict based on the number of texts. So that's going to be our total cost. Okay, it's kind of funny saying we're predicting it in this sense because it is an actual formula for it, but it still fits the model of the thing we get to choose, number of texts, the thing we measure, total cost. Okay, so independent, dependent. Now remember, independent variable, we want to use x for that, the horizontal axis, and the dependent variable we're going to use y for. Okay, so we already wrote this one way. We said y, the total cost, is equal to 40 plus 0.15 times the number of text messages. Okay, and we could also write that this way, right? We could do the text message cost first and then think about adding the $40 basic fee. When we went to go calculate it in part 1, probably thought more of it this way. I'm going to take the 40 and then I'm going to add something to it, okay? Rather than thinking about what is getting added and then adding the 40. But you might think either way. So both of these are correct. Now this is y equals mx plus b, where b is the y-intercept and m is the slope. This curriculum is going to refer to this as a plus bx. But don't be confused because in this context, b is the slope and a is the y-intercept. So it's just a different way of writing it, but it's definitely a linear relationship. Okay, so what does the 15 cents represent in this relationship? Okay, so the 15 is the slope of the line, right? It's the slope, we could say it's the rate of change. Okay, it's how the total cost is changing. So it's the rate of change, or it's the slope. And it is, we could say, total cost increases by 15 cents for an increase of one text message. Okay, so for every one text message increase, the total cost increases by 15 cents. Okay, so whenever you describe the slope in these relationships, you have to say, you're really referencing both variables, right? In that statement, I referenced total cost and one text message, okay? Explain what $40 represents in this relationship. It's the fixed cost. $40 is the fixed cost. Okay, that part, it's the part that I pay even if I don't have any text messages. And it's going to be the y-intercept too in this linear function. Okay. All right, now you're going to sketch a graph on this grid, and you already have some values that you could plot. The first one is right here. Get it right. 0 text messages. I'm going to pay $40. So go ahead and graph a couple more points and then come back and check it against mine. Unless you already have, you can just keep watching. Okay, so I've plotted 0, 40, and then 250, 77, 50, and I'm going to draw the line between those. So it's a straight line whose slope is 15 cents per text message, and this would show values for different numbers of text messages. So we would want to label these grids. Number of texts is our independent variable. Whoops. And sorry. I need the full screen. And our dependent variable here is total monthly cost. It's always good to, and that's in dollars. It's always good to label your axes for a graph. Oh, and it even said to do it. Clearly label the axes and include units in the label. So total monthly cost in dollars and number of text messages sent. Okay, our next exercise is number 10, and it's, let's read it. Lemoyne needs 4 more pieces of lumber for his scout project. The pieces can be cut from one large piece of lumber according to the following pattern. The lumberyard will make the cuts for Lemoyne at a fixed cost of $2.25 plus an additional cost of 25 cents per cut, and one cut is free. Okay, so the first cut they'd make for free, so maybe this one. Then Lemoyne would have another cut here, and then they'd need to cut this piece right here. Okay, so this is a relationship. The total cost for the cuts is going to depend on the number of cuts that you need. Okay, that makes sense. What is the functional relationship between the total cost of cutting a piece of lumber and the number of cuts required? So let's, we could do this a couple ways. We could let X be the number of cuts required. Okay, so if we let X be the number of cuts required, then what will that function be? So think about that for a minute. Okay, so like we said, I'm going to define one more variable over here. Let Y be total cost. Total cost for getting the cuts. So X is the number of cuts required, Y is the cost, okay? So we can write this functional relationship. The total cost is going to be $2.25 plus the additional cost of 25 cents per cut after the first cut. So I don't have to pay for all X cuts, but I do have to pay for X minus 1 cuts, okay, because one's going to be free, and then I'm going to multiply that by 0.25. Okay, I want to write this another way. I could also think of it this way. Because that first cut is included, I could really think of it this way. I could say I have to pay $2. The 25 cents is going to be my first cut, plus X times 0.25, or 0.25 times X, however you want to write that. So in the second case, I'm kind of thinking, well, I just want to multiply by X, the number of cuts, times 25 cents. But since one of them was free, my flat rate's really only $2. And if you simplify this equation, it's the exact same thing as this equation once it's simplified out. So we could do that. The other thing we could do with this problem is to define a different variable. So let's get some pages to do that. We could let X be the paid cuts, how many I have to pay for. Okay, if X is the paid cuts, then the total cost is going to be 2.25 plus 0.25 times X. Okay, so this kind of points out how important it is to define your variable because this X is not the same as this one. In both of these functions, X is the total number of cuts required. So for this project, it'd be 1, 2, 3 cuts. But in this function, X is just the ones I have to pay for. So the one, it's already been subtracted. Okay, so let's, there was one more part to that. Okay, so here's the rest of exercise 10. Okay, so we're going to use the equation to determine Lemoyne's total cost for cutting. So let's use the one y is equal to, I'll use the simplified one, 2 plus 0.25 times x, where x is the total cuts required. So for this one, remember we said we had to make 1, 2, 3 cuts. So go back there. So x equals 3, so y is equal to 2 plus 0.25 times 3, which is 75 cents. So y is equal to 2.75. Okay, not too hard for us to have figured out on our own without a function, but if you wanted to program this, once again, you would need to know the function to be able to do that. Okay, so now interpret the slope of the equation in words. What is the slope of that equation and what does it mean? Okay, so 0.25 or 25 cents is the slope. Okay, so another way to say that is the total cost increases by, increases by 25 cents for each additional cut. Okay, and this description works for either of the ways we define the function. Each additional cut increases the total cost by 25 cents. Okay, so it's the rate of change, it's the slope. Interpret the y-intercept of your equation in words in the context of this problem. Does interpreting the intercept make sense in this problem? Okay, so in the cell phone example, having 0 text messages made sense. But in this example, having 0 cuts, we're not going to have to pay that $2.25 if we make 0 cuts. So there is no fixed cost in that sense. So it only so the y-intercept doesn't have really any meaning in the context of this problem, because $2.25 is the least that you would pay, and you would get 1 cut for that amount. Okay? All right, so the y-intercept doesn't always have to really make sense in some of these problems, especially in some of our scatter plots. Okay, last example. Omar and Olivia were curious about the size of coins. They measured the diameter and circumference of several coins and found the following data. Okay, so they measured a penny, a nickel, a dime, a quarter, and a $half. They got the diameter in millimeters and the circumference in millimeters. Wondering if there was any relationship between the diameter and circumference, they thought about drawing a picture. Draw a scatter plot that displays circumference in terms of diameter. Okay, so let's just talk briefly about what variable do we want to use for our independent and what variable do we want to use for our dependent. So let's read what it says. We want to display circumference in terms of diameter. So what that's going to mean is that our circumference is going to be over here. Basically, we could think of predicting the circumference in terms of the diameter or based on the diameter. Okay, this relationship could really be graphed either way. We can also predict the diameter based on the circumference, but this is what they asked us to do. So we're going to draw a scatter plot that that is going to have diameter as the independent variable and circumference as the dependent. Okay, so you can pause and work on that. You're going to be eyeballing some of these, so come up with a good scale and for your x and y axis. Okay, so your graph might look something like this. This one, notice that they have not started at 0, 0 because the smallest diameter they had was 18 and the smallest circumference they had was in the 50s. If you start at 0, 0, that's fine. You just wouldn't have had any points in this part of the graph. But it would still show this pattern in the data. Okay, so do you think that circumference and diameter are related? Explain. Okay, so looking at our graph, do you see a relationship? Well, yeah, you could say, I see a pretty clear linear model going on here. They all appear to be in a line. Okay, so we could say there appears to be a linear relationship between the two. And if they're not exactly in a line, it probably has to do with a measurement error or rounding of the variables. Okay, so part C says, find the equation of the function relating circumference to the diameter of a coin. Okay, so what we're going to do is pretend that we don't know what the relationship between circumference and diameter is, but hopefully you do remember that. But let's go back and look at a couple of the data points. So we'll use these first two, and what we're going to do is find the slope, and then we can also interpret the y-intercept. So let's look at what the slope of that is. So if I want to find the slope between these 2 points, I'm going to get 66.6 minus 59.7, the difference in y, over 21.2 minus 19. So this is equal to, down here we've got 2.2. And on top we have 6.9. So when I subtract those two. All right, so, and if I divide this out, I get, let me check it again, 3.136, repeating, 3, 6, and so on. So this is approximately, we'll round it off to 3.14. Does that look familiar to anybody? Okay, and so then, so we know this is a linear relationship, so we're doing y is equal to mx plus b. So we've got 3.14 times x plus b. So we'll put a point in. We'll put one of these points in. Y is 59.7 is equal to 3.14 times 19 plus b. And so this is 59.7 is equal to, and this multiplied out is 59 and 66 hundredths, 59.66 plus b. So b is equal to 0.04 here, which is approximately 0. So the equation that we have, let's get our new color, the equation that we have is y is equal to 3.14 times x. All right, and let's talk about what y was. Y was the circumference, 3.14. X was the diameter. So the circumference is pi times the diameter, right? Pi times the diameter. So our data, just using our data, we were able to come up with the formula for the circumference of a circle. Okay? Okay, now in D, the value of the slope is approximately equal to the value of pi. Explain why this makes sense. Okay, and so that's kind of what we just talked about, because pi is used in formulas for circles. For area and circumference formulas for circles. Okay, so that's could be a reason why that makes sense. What is the value of the y-intercept? So the y-intercept equals 0. Explain why this makes sense. Okay, the y-intercept is the value of the y variable when x is 0. Okay, so we could say a circle with a diameter of 0 has circumference equal to 0 as well. So if the diameter is 0, the circumference is 0, and that's where we get that, the 0, 0 y-intercept. Okay, so if we extended this line here, it would intercept at 0, 0. Now it's not looking like it would on this graph, but that's because of this issue here with how we've drawn the scale on the x and y axis. But the y-intercept is actually 0. Okay, so let's summarize this. So a linear functional relationship between a dependent and independent numerical variable, so we've got two variables, has the form y equals mx plus b, which is what we've been using, or y equals a plus bx, which we saw an example of writing it that way. But remember, if I'm going to write it this way, the slope is always the coefficient of the independent variable. So the coefficient of x is the slope. So in this case, when it's written like this, the b is the slope because it's the coefficient of the x variable. Okay, in statistics, a dependent variable is one that is predicted, and an independent variable is the one that is used to make the prediction. Okay? So it's the predictor and the predicted, once again. So the graph of a linear function describing the relationship between two variables is a line. All right, we've seen that many, many times. Okay, so you've got a couple different problems to work on in your problem set where you're going to be finding equations and determining which variable you want to use for the independent and the dependent. Okay, so good luck with that, and we'll see you back for lesson 11 where we'll be doing more scatter plots.